Okay. So, now the difference between arrestor discharge characteristics and equipment withstand level at any given instant of time is called the margin of protection, and this is your this actually margin of protection, this is actually margin of protection, right. So, it can be expressed as MP is equal to BIL equipment minus VAR divided by BIL equipment, that is basic impulse insulation level. So, BIL equipment is the BIL of the for the equipment, whatever equipment you are testing, and VR is the discharge of voltage of the arrestor, and generally MP is greater than equal to 0.20. That means, if this value if you make it MP, so it will be greater than equal to 0.20. This is your what you call that your withstand your discharge, the difference between arrestor discharge and this one is called the margin of protection. In short, they call MP, the margin of protection, right. So, with this that your transient over voltage and insulation coordination is over, right. Next, all these things after this whatever will come, first next will come the corona, that is your corona loss, right, in transmission line. So, after this all these things we will find things are very interesting, like next corona, then sag and tension will come. After that your distribution system will come, whatever possible in the classroom that we will proceed. Then load frequency control and unit commitment, you will find things are, we will find that things are very interesting. So, corona. So, we will start from corona loss, generally you know, you have some ideas, right. So, basic introduction is the use of high voltage is extremely important, right, in order to meet the rapidly increasing power demand, right. So, the corona characteristic of generally corona happens that line having voltage level 220 kV or above, right, your assume great importance, particularly in that your what you call, later I will come to that, in the rainy season or or any other time also you can see the corona is happening and line 220 kV or above. So, investigation on the basic your basis of series of experiments reveal that it is possible to predict corona performance of transmission line under various operating conditions. So, at different operating conditions corona can be predicted, but later we will see that corona loss computation, those formulas basically empirical formulas based on the field test people have made it over the years, and corona actually has associated power loss, power loss due to corona is okay, right. The radio and TV interference and audible noise, right, this is actually corona causing power losses, same time radio and TV interference and audible noise. Another thing is that later will come, due to corona that your voltage and your current waveform become non-sinusoidal, right. So, corona plays an important significant role, particularly in power loss thing, but exact evaluation is not possible, but some empirical formulas will be there from the field test, later we will see that. So, and in this chapter also we need little bit of your knowledge of those capacitance chapter, that which we have seen in power system analysis course. So, directly some equations from there I will write, because those equations are needed instead of telling, but I will refer that thing to that your capacitance chapter of the power system analysis course, right. So, corona influences the line losses and the design of overhead transmission line conductors, hardware and insulators, because you have to consider all sort of things such that your what you call that your you have to design the transmission line, because corona actually causing transmission line losses. Whatever phenomena here we will consider, that is for round conductor, that is cylindrical in shape, that we say, but suppose if we take some kind of logical problem, that suppose instead of round conductor, if you choose a rectangular or square cross section conductor, then how the corona will be formed. This is a question to you, answer I will not give, that you write to me, that instead of round conductor, if we take a conductor having cross sectional is a square or rectangular whatsoever, then how will be the corona loss, right. So, now the phenomena of corona, basically air is not a perfect insulator, that you know, right, and even under normal condition the air contains a number of free electrons and ions. Now, if you consider two large parallel conducting planes or conducting path, right, if you assume and apply voltage across these two, that means when an electric gradient is set up between them, right, you apply a potential across them, right. The electrons and ions acquire motion by this because electric field will be created, and your electrons and ions, right, both will acquire speed or motion, and they maintain a very small current between the conducting planes. So, that means if you consider two electrode and you are applying voltage across this, so electric field will be created, and in that case what will happen, that electrons and ions acquire motion by this electric field, and this maintain a very small current between the conducting planes. So, between these two it will maintain a very small current. So, current is negligible when the electric field intensity is less than 30 kilovolt per centimeter, but this if this potential gradient is less than 30 kV. So, this current is very small, right. But when the electric field intensity or potential gradient reaches the critical value, say 30 kV per centimeter, therefore, while you have the air in the immediate vicinity of conductors no more remains a dielectric at that intensity. I mean, when it reaches to 30 kV per centimeter, the potential gradient, then air surrounding the conductor will never remain as a dielectric, and at this intensity the ions or attain high velocity, right, and striking other neutral electrons molecule rather, right. So, in that case what will happen, that it is striking another neutral molecules and dislodge one or more electrons and from the neutral molecule. That means, this produces a new electron and a positive ion, and this process is a continuous process. So, which are in turn accelerated and collide with other air molecules to ionize them further. So, it is a continuous process, and it will produce your what you call more your new electrons and positive ions, right. Thus, the number of charged particles goes on increasing rapidly. This is true. This happens only if the potential gradient around the conductor reaches 30 kV centimeter or above. If a uniform field intensity, suppose if you assume uniform field intensity between the electrodes, just now I showed two paths, right, then such conditions are produced everywhere in the gap. If electric field is uniform, say between the two paths, then at every point such activity will be your what you call your that uniform field intensity, then between such conditions are produced everywhere in the gap. Now, as a result of this, the saturation will be reached, and therefore, the air becomes conducting. In that case, that air will become conducting, hence a complete electric breakdown will be there, and it occurs an arc and is established between the two electrodes. That means, basically suppose it is same way we will consider, suppose you have two electrodes or two path, or two parallel plane, thus you apply the electric field, apply the voltage across these two, and electric field will be created. And if you assume that everywhere that is electric field intensity is uniform at every point, then there will be a breakdown at this voltage, the potential gradient 30 kilovolt per centimeter, right. So, in that case what will happen, a complete electric breakdown and arc is established between the two electrodes. So, I think in those who are doing high voltage laboratories, they might have seen this kind of phenomena for different experiment in the high voltage laboratory, right. Even it is not only that plane between two sphere also, I mean whatever it is, it will happen, and you can see that if you increase the potential gradient, that breakdown will happen. It is high voltage laboratory. If you see that you can see that through experiment, maybe many of you might have seen in your college in the high voltage laboratory, right. So, when an alternating potential difference is applied across two conductors, like we are thinking about your what you call that overhead transmission line. So, when you apply that your alternating potential difference, that is AC voltage, right, between two conductors whose spacing is large in comparison to the radius or diameter of the conductor, right, then the air surrounding the conductor is subject to electrostatic stresses, right. This is known to you. Now, the stress or intensity is maximum at the surface of the conductor, that we know. For the cable studies, when we are studying that cable, electric stress, we have seen potential gradient Q divided by 2 pi epsilon 0 in R, at x is equal to R, that stress is maximum, right, and it decreases in inverse proportion of the distance from the center of the conductor, and if you move along that, it is inversely proportional to the distance, that we know. Now, if the potential difference is gradually increased, I mean, if you go on increasing the potential difference, then a point will be reached when a faint luminous glow of violet color will make its appearance, and at the same time a hissing noise will be heard. Now, two conductors are there. If suppose potential your difference gradually if you increase, right. So, a point will reach when you will find that from your what you call a faint luminous glow of violet color will make appearance, that is makes its appearance, that is around the conductor you can observe that, right, some luminous glow and with violet color, and at the same time a hissing noise will be heard. And another thing is that you will find that your what you call characteristic odor, that is their ozone gas, right. So, this phenomena is called corona and is accompanied by the formation of ozone, right. This ozone will be formed as is indicated by the characteristic odor of this gas. So, from that you can find out that this is ozone actually ozone gas from its smell you can find out, right. So, basically this is your basic philosophy of corona, right. So, question is that this I do not know whether you might have seen corona or not, particularly if 220 kV line, if the if of course it will be if around that suppose in a village, suppose high tension line is going on, suppose no light is there surround, you can see that luminous glow around the conductor, and rainy season it will be more visible. I have seen many places that it is happening. It doesn't night time it will be visible, daytime it also it is happening, but daytime you cannot make out all the time, but that some chattering noise will be there. From that noise you can make out that corona this is due to the corona only. You will find some kind of noise for 220 kV line or above, right. And if you hear the noise, that hissing noise, then you can find yes corona is happening. This is common phenomena for transmission system. So, this luminous glow is due to the fact that the atmospheric air around the conductor become conducting, because it is ionized, right, due to the electrostatic stress, because around that conductor, that air your what you call that air around the becomes conducting, right, but potential gradient has to be very high, 30 kilovolt per centimeter or above. So, if the potential difference is raised still further, if you go on increasing the potential difference, then the glow and noise will increase, very common, right, in intensity until eventually a spark over will take place, right. If you go on increasing this thing, then a spark over will take place between the say conductor, but generally for transmission line, for your what you call in laboratory you can go on increasing if you have that your what you call laboratory facilities, but for transmission line in general your what you call that under normal operating voltage it may be 220 kV or above, right. So, there you cannot do that unless and until some abnormal things happens, right. If the conductors are perfectly uniform, now we are assuming the conductors are smooth, right, a round shape conductor, we are whatever we are talking about the uniform or what you call the cylindrical conductor, the circular cross section, but I gave you a problem that if it is not circular, if it is your rectangular or square cross section, then how the corona will be formed. Another thing is, if conductor is not a solid, if it is a hollow conductor, then how that corona will form, this is a question to you, right. The glow will be uniform along their length, otherwise the rough points of the conductor will appear brighter. I mean, if conductor is actually conductor surface is not smooth all the time, some rough points also will be there, wherever rough points will be there, that your what you call that luminous glow will be much brighter than the smooth portion of the conductor. So, with conductors only a short distance apart in comparison with the diameter, the spark over may take place before there is any luminous glow is observed. That means suppose if the distance between two conductors is less compared to its diameter, then before it luminous glow you can observe, spark over may take place. That means, if you bring two conductor very close to that and a potential difference you go on increasing, then spark over will take place before you can before anything you observe, right. I mean, luminous glow or anything, the spark over can take place. So, if the applied potential difference is a DC, this is a question to you, I will only mention, but answer you should give it to me. If the potential difference is DC instead of AC, suppose we are applying now DC voltage instead of AC, the positive conductor having a uniform glow. The positive conductor will have uniform glow, while the negative conductor has a more patchy glow, and often it is accompanied by streamers if there are any rough places. Streamer means if rough places, if it is a jumping streamers, right. So, question is that the positive side is, if it is a DC, it is uniform, whereas negative side is a patchy, or if it is a rough surface is there accompanied by streamers if there are any rough places. This is a question to you, that for DC why for positive side is uniform and why negative side is like this, right. So, this is a question to you. So, an important point in connection with the corona is that it is accompanied by loss of power. This we know, there will be power loss, right. So, loss of power which is dissipated in the form of heat, the light, sound and chemical action. Chemical action means ozone gas, sound means hissing noise, your light means your what you call luminous glow we have seen, and heat means if power loss is there, that heat will be generated, right. So, these are all sort of outcome from corona, right. Now, in case of AC system, of course, all the overhead transmission line apart from HVDC line, basically all are AC system. Current flow due to corona is non-sinusoidal, and in practice this non-sinusoidal current and non-sinusoidal voltage, right, drop by corona may be more important than the power loss. So, sometimes it causes problem, but corona also it contributes significant of that portion of the power loss. Now, therefore, the effects of corona can be summarized in a few points. Look, it is accompanied by power loss, this is known to you. A luminous violet glow is observed around the conductor, right. This glow is much brighter over rough and dirty surfaces of the conductor rather than smooth surface. It produces a hissing noise, it produces ozone gas which can be readily detected by its characteristic odor, right. So, these are few points can be summarized for corona, right. So, you can that is why I am telling that try to see, if you see any overhead line 220 kV or above, you can see this corona things. Now, with this we will come to the potential gradient for single phase line, all related to corona. Now, this thing actually potential gradient for single phase line, that again I will refer that that capacitance chapter, everything has been done there for power system analysis course. When you will study, these are very simple thing, but if you want to recall your memories, then please you see that see that capacitance chapter, right. So, this is suppose it is a single phase line. So, this is conductor 1, this is conductor 2, this carrying charge plus q. So, hence it is a minus q, and take in between some point p. P is the distance from this conductor, that is x, and then this total distance between these two conductor 1 and 2 is d. So, if it is x, this will be d minus x. So, there is a single phase transmission line say we are considering, right. So, radius of each conductor we are assuming that it is r, both are r and r. If it is different also, that has been also covered in your capacitance chapter, right. So, the voltage gradient at point P from conductor 1 is given by, say, from conductor is generally G is equal to capital G is equal to capital G 1 minus G 2. So, this is equation 1, say, where G 1 is voltage gradient at this point, voltage gradient at point P due to charge plus q on conductor 1, right. So, this is G 1. Similarly, G 2 the voltage gradient at point P due to charge minus q, right, on conductor 2. So, G is equal to actually G 1 minus G 2. So, potential gradient, right. Now, one thing you know, potential gradient in cable chapter we have seen that it is q upon 2 pi epsilon 0 x, right. Therefore, we know that G 1 is equal to q upon 2 pi epsilon 0, this is volt per meter, right, and G 2 is equal to your minus q upon 2 pi epsilon 0 d minus x volt per meter, right, because this we know G 1 is equal to 2 pi epsilon 0 x, and for G 2 it is minus q divided by 2 pi epsilon 0 d minus x volt per, these are potential gradient, right, potential gradient. Now, and G is equal to G 1 minus G 2. So, this G1 and G2 you substitute in this equation and G2 is minus q upon this thing. So, when you submit G2 is equal to minus q, this sign will become plus, right. Therefore, your G is equal to q upon 2 pi epsilon 0 x plus q upon 2 pi epsilon 0 into d minus x, right. Therefore, G is equal to q upon 2 pi epsilon 0 common, you take common, it is 1 upon x plus 1 upon d minus x volt per meter. Now, the voltage gradient is maximum at the surface of the conductor where x is equal to r. This we have seen for cable also, at x is equal to r the voltage gradient is maximum. Now, if you substitute x is equal to r in equation, you will get, suppose if you substitute x is equal to r in this equation, then you will get just one this thing, you put x is equal to r here, right, because it is maximum. So, if you do so, then in this equation if you put x is equal to r, it will be 1 upon r plus 1 upon d minus r volt per meter. Therefore, it will be your 1 upon r plus 1 upon d minus r, right. Since d is large as compared to r, right, radius. So, we can write d minus r approximately d, therefore, we can get G max, because x is equal to r, it will max, it will be q upon 2 pi epsilon 0 r volt per meter. This equation can be written as q upon 2 pi epsilon 0 r volt meter. How it is happening? Actually, it is 1 upon r plus 1 upon d minus r, right, is equal to d minus r, right, plus r divided by r into d minus r. R cancel is equal to d upon r, then d minus r, but d minus r approximately is equal to d, right. Therefore, it is d upon r d, dd will be cancelled, it is 1 upon r, right. That is why that this whole expression, this expression approximately is equal to 1 upon r, that is why q upon 2 pi epsilon 0 r, right. So, volt per meter, here I have made it here also, same thing, same calculation I have made it here, right. Therefore, the RMS value of voltage gradient is given by, this is maximum value, then that is why instead of this G max is equal to q upon 2 pi epsilon 0 r volt per meter. The RMS value is G RMS is equal to G max upon root 2, right. So, potential difference V12 between the conductors of a single phase line is written as, this has been for capacitance calculation, this has been derived in the capacitance chapter in power system analysis course. So, directly we are writing, right, directly we are writing that your V12 is equal to q upon pi epsilon 0 ln d upon r, referred to that capacitance chapter power system analysis, right. Directly I am not wasting time here again doing this, this already has been done and available with you. So, this is q upon pi epsilon 0 ln d upon r volt, this is equation 8. Now, voltage from conductor to neutral is given by, basically it is single phase line. So, we can make it V n is equal to, suppose if you have a neutral, for example, suppose the neutral is available. So, it will be V12 upon 2. So, it will be q upon, then it is 2, it was q upon pi epsilon 0, now it will be q upon 2 pi epsilon 0 ln d upon r volt, this is equation 9, right. So, equation 9, then this equation 9 can be written as this equation, actually both sides you divide by r, right. Then this one can be written as V n upon r is equal to q upon 2 pi epsilon 0 r ln d upon r. Actually, this equation is divided both sides by r. Therefore, this q upon 2 pi epsilon 0 r can be written as this one, q upon 2 pi epsilon 0 is equal to, right, is equal to, it will be V n divided by r, and this ln d r ln d upon r will come here. So, V n upon r ln d upon r, right. Therefore, this is actually G max, because G max is equal to your q upon 2 pi epsilon 0 r, this is actually G max from equation 6, q upon 2 pi epsilon 0 r, right. Therefore, your G max is equal to V n upon r ln d upon r volt meter, this is actually equation 10, right. So, from that we can get maximum your potential gradient, that G max will be V n upon r ln d upon r, right. So, This is for your single phase line. Now, for 3 phase line, 3 phase again this derivation again I will refer to your then capacitance chapter, all these things derived there. Suppose you have a 3 phase line A, B, C, 3 conductors are there, and distance between 2 conductors is, for example, AB is DAB, BC is DBC and CA is DCA. So, it is unsymmetrical 3 phase transmission line, we are not considering symmetrical, say unsymmetrical, right. And you know that DEQ equivalent is DAB, DBC, DCA whole to the power 1/3, that you know. So, figure 2 shows the unsymmetrical 3 phase transmission line, this one, right. Now, you assume that let GA, GB and GC denote the voltage gradients at the surface of the conductors in phases A, B and C. So, A, B and C, GA, GB, GC, right, are the potential gradient of the conductors A, B, C, right. Therefore, we can write QA upon 2 pi epsilon 0 is equal to R into GA. Basically, you know this one, no? That you know this one, that GA, for example, for phase A, GA is equal to QA divided by 2 pi epsilon 0 R. We are assuming that radius of all A, B, C 3 conductors are same R. We are assuming that, right. So, that means GA you can write for conductor in phase A, right. GA is equal to QA upon 2 pi epsilon 0. That means we can write QA divided by 2 pi epsilon 0 is equal to R into GA. This one similarly your QB upon 2 pi epsilon 0 is equal to R into GB. Similarly, QC upon 2 pi epsilon 0 is equal to R into GC, right. That means therefore, that is why we are writing here that QA upon 2 pi epsilon 0 is equal to R into GA. Similarly, we are writing QB upon 2 pi epsilon 0 is equal to R into GB. This is equation 11, this is equation 12. Therefore, and similarly QC is equal to your QC upon 2 pi epsilon 0 is equal to R into GC. This is equation 13, right. Now, this voltage VAB is given by again from the capacitance chapter, directly I am not deriving it again, but everything is there in that capacitance chapter, all I have done there, just have a look again, that is all if you have forgotten. So, VAB is equal to QA upon 2 pi epsilon 0 minus QB upon 2 pi epsilon 0 into ln DAB upon R plus QC upon 2 pi epsilon 0 ln DBC upon DCA, right. So, therefore, this numerator and this thing, or what you call this VAB is equal to, it is your if you make multiply by R, then it will be GA minus GB. I will tell you how it is coming, GA minus GB ln DAB upon R plus GC ln DBC upon DCA volt, right. Similarly, your VAC also R GA, I will come to that how it is coming, GA minus GC ln DCA upon DR plus GB ln DBC upon DAB volt, right. So, this is actually equation 15. So, from this how we are coming, I will be coming back. Thank you.